Okay, hi folks. My name is Matt Thomas, and thank you for tuning in to the USGS Landslide Hazards Seminar. This meeting is hosted by the Landslide Hazards Program and co-organized with contributions from Stephen Slaughter and Jamie Kostelnik. For those of you that are new to this meeting, you have the ability to submit questions via the chat window or to use the raise your hand feature in combination with your microphone and video camera. We're going to wait until the end of today's presentation to take questions. So in the meantime, please just do your best to make sure your microphone is muted when you're not intending to speak. It's my pleasure to introduce today's speaker, Seth Moran. Seth graduated with a geology degree from Oberlin College in 1988. He found himself increasingly interested in the here and now and then shifted over to geophysics for graduate school, earning a master's and PhD from the University of Washington for research projects looking at seismicity at Mount St. Helens and Mount Rainier. He was hired at the USGS in 1997 to do work as a research seismologist at the Alaska Volcano Observatory in Anchorage. And in 2003, he transferred to the Cascades Volcano Observatory in Vancouver, Washington. After serving as a scientist in charge at CVO between 2015 and 2020, Seth returned to the research and monitoring world. He's currently serving as a project manager for the Rainier Lahar Detection System project and the acting EnViews program coordinator. Outside of work, he likes to play the fiddle, hang out with his family, and go on long walks with his poodle, all of which sound like nice things. Seth, thank you for joining us today.
You bet, and thanks everybody. Thanks for having me. And I want to start off by acknowledging the folks that I've listed on this screen, all of whom have been significantly involved in various parts of this project, and many of whom work is reflected in slides. And I'll try and acknowledge them, remember to acknowledge them as I progress. What I hope to do today is to give you all a sense of this project, the Rainier Lahar Detection System project, which is something that the USGS has been engaged in for several decades now as one part of risk mitigation strategy that's been followed by USGS and other groups that are representing the communities that live around Mount Rainier as one way of addressing this unlikely but potentially catastrophic hazard that I'll introduce here in a little bit. So a quick overview of Mount Rainier. It's an active volcano. It's erupted 40 times at least in the last 10,000 years, most recently about 1,000 years ago. The eruptions have not been very explosive, and that's an important thing in terms of thinking about the next eruption and what are we going to be worrying about. The largest eruption in the last 10,000 years in terms of ash production occurred 2,200 years ago. It was about 10% the size of Mount St. Helens 1980. And what I'm showing here is a model run from courtesy of Larry Maston from here at USGS CVO. As part of that, he ran using his program called ASH 3D that took the volume from that 2,200 years ago event and put it up into the atmosphere with winds that were blowing from the southeast on a day when the wind field's coming from the southeast. This shows kind of the worst case scenario for ash impacting the most people. This is something that goes along the axis of the urban corridor of the Puget Sound. A similar size eruption with the winds blowing in that direction could put between 1 millimeter and 1 centimeter of ash in the SeaTac urban area, which is definitely a nuisance, but it's not life-threatening. The real big hazard attached to Mount Rainier is large lahars, what we call large lahars, which are lahars that can reach into the Puget lowlands in areas that have now rapidly growing populations. At least 11 of those have reached into the Puget lowlands in the last 6,000 years. Over 90,000 people live in Rainier Lahar hazard zones. The most recent large lahar occurred in about 1507 AD. It's the so-called Electron Mudflow. That date in my career has become increasingly precise, courtesy of some really cool tree ring dating that's been done in the last couple of years. And there's going to be a publication coming out at some point that will have that date more kind of ironed out. 10 of these 11 large lahars were associated with eruptions. So that's an important thing, is that the most likely way that we get a large lahar is Mount Rainier erupts, hot stuff on top of cold stuff, very high volcano, and lots of momentum bringing it down into the lowlands. But this last one, this 1507 AD Electron Mudflow, was not apparently associated with an eruption. There's no geologic evidence of there having been an eruption. Doesn't mean there wasn't an explosion, doesn't mean that there was a really, really small eruption for which there's no geologic evidence. But we do know that it started by a landslide, and it's definitely a possibility that it just was a landslide that transformed into a lahar. And that's really the focus of this project, is that specific hazard. This graphic, USGS graphic, gives you a sense of the lateral extent of some of these large lahars, and I'll call your attention to the purple color, which shows the extent of the electron mudflow. And what I've got here in yellow are the population, most recent census population estimates for two towns that are on top of these deposits: the town of Ording, 9,000 people, and the town of Sumner, 10,500 people. And this photograph that's taken from the northwest looking southeast across Ording and towards Mount Rainier gives a pretty visual sense of the problem. The valley that most of these the people are living on the valley floor. The valley walls are fairly steep, and most of these 9,000 people are, in fact, vulnerable to this hazard. And a lot of the houses that are in that picture, the foundations dug into deposits from the electron mudflow. So a really super important question to be able to address is, could another one of these large lahars happen without an eruption at Mount Rainier? And this graphic is from a paper by Mark Reed and others in 2001. And it's the combination of several research projects or research groups that were collectively looking at the question of what is Mount Rainier made of. There's a quote from Carol Finn and others, 2001, who did aeromag survey around the volcano. And they have this nice little statement that there's appreciable thicknesses of mostly buried hydrothermal altered rock that lie mainly in the upper west flank of Mount Rainier, which is the source area for the electron mudflow. And they say that that's the likely source for future large debris flows / lahars. And then from the Read It All paper, they have this statement that this area could, again, in the future, produce another sizable flank collapse that they say is greater than 1/10 of a cubic kilometer. That's promoted by this area of hydrothermally altered rock. And the graphic on the right-hand side, there's a sort of orange and red bullseye that this is from Mark Reed's, this is from his slope stability analyses that married the geologic and geophysical understanding of the compositions of the edifice with basic slope analysis. So the good news from all of this work is that the northeast and south sides of Mount Rainier are pretty competent rock, and this possibility of a landslide occurring on its own, transitioning into a lahar, is really not a hazard, not a thing. That becomes an issue. The other parts of the volcano become an issue when the volcano wakes up, and then hot stuff and cold stuff that can send lahars down pretty much any drainage. So the bad news is this conceivably, yes, could happen, and the hazard's really focused on the west flank. So then the question becomes, well, what happens if this happens again? What kinds of timescales are we talking about? How far would it go? What kinds of flood inundations would be looking at? David George, Dick Iverson, and others developed a fairly sophisticated multi-phase fluid flow model that is called the DCLAW model. And as part of this, they ran some scenarios at Mount Rainier, taking patches of this western flank, the Sunset Amphitheater area, and letting them fail, and then mapping out the results. So this is a volume, 260 million cubic meters. That's about the equivalent size of the volume estimated for the electron mudflow. They also assigned it a high mobility, which is important because that's a significant variable in how far these lahars will go. And I'm just going to step through a couple of these to give you a sense. Here it is at 2 minutes. And Ashford, the Nisqually, so at 10 minutes, it hits the Nisqually entrance, which is the southwestern entrance into Mount Rainier National Park. It's by far the most popular entrance, and also that's where Mount Rainier National Park staff live year-round. At 20 minutes, it's reached into the town of Ashford, which has about 500 people living in it year-round. And then at 60 minutes, It's gone further down the valley on the Nisqually side of things, on the Ashford Park entrance side of things, but it's also continued on towards Ording. And this gives you a sense of the timings. We're talking tens of minutes before it gets into places that are lightly populated, and within 60 minutes or less to areas that have lots of population. So this hazard, although our understanding of it has sort of been increasingly refined and improved over the space of the last several decades, the broad strokes of this hazard were understood in the 90s. And USGS worked with several agencies in Washington to develop and put together and install the Rainier Lahar detection system, what I'm calling version 1. This was installed in 1991. And a prime design element of this is that there were separate detection and warning components. The USGS, Cascades Volcano Observatory, Andy Lockhart, Tom Murray primarily designed and installed the detection component, which consisted of 6 acoustic flow monitoring stations and several tripwires on both the Puyallup and the Carbon rivers, and then also detection software that was based on RSAM values and also on the tripping of the tripwires that ran on computers that were running in 2 separate 24/7 emergency operation centers, or EOCs. Those EOCs are operated by state and county emergency management agencies. They have staff there 24/7, and they have the responsibility of the warning. This is a very important distinction that USGS is not our lane, at least in this context, for doing all the things that are needed to get word out to people and to give them actionable information. Things like reverse 911 and sirens and whatnot. All that is changing, and our folks that we're working with have a lot more experience using these systems just in day-to-day life. So this has been integrated into their sort of routines. In the field, this is a schematic of what a typical station looked like. It had a geophone that was attached to a equipment box that had a radio. And then there's the tripwire that had that was attached to a float. And the idea is the water came through, floated the float, broke the cable, and that plus basically an RSM type trigger would, on multiple stations, send a detection to these EOCs, and then they would take it from there. Here's a map. So Mount Rainier is just off to the southeast, to the lower right-hand corner of this picture. And I've circled these yellow diamonds that correspond to the locations of these AFM/tripwire stations, and you can see they're both on the Puyallup and the Carbon rivers. The reds and the pink colors correspond to flood inundation estimates for different sizes. The red is 40 million cubic meters, pink is 250 million cubic meters. So there were some definite limitations with these systems. First of which was they didn't transmit data in real time. Only 2-minute RSM values were transmitted. And that reflects technological limitations of the day. This was back when digital radios were just becoming a new thing, and really isn't a telemetry infrastructure out in the areas where these stations were installed. So having things that were very low bandwidth was important. But this also put a delay into any kind of alert. The reason for that is that this software was designed to be very fault intolerant, really trying hard to avoid false alarms for understandable reasons. And so one part of this was to have a requirement that there be 2 successive detections required before any alarm would be issued in the EOCs, triggering those folks to start doing the warning thing. And this put a total of at least 4 minutes in delay between when the Lahar would go through this network and then the alert would go off. And as the modeling suggests, 4 minutes is a lot of time when it comes to giving people enough time to get out of the way. Also, because there was no real-time data, there's no situational awareness. You couldn't look at the data and see what signals were causing this alert to go off or this detection to go off. And also, there was no way of knowing if the sensors were still functional. And that is just a factual statement. Another limitation was that they were only using short period single component sensors, so not recording the full spectrum of seismic motions and being able to take advantage of the full spectrum of seismic motions. And also was not integrated with the Rainier Volcano Monitoring Network. So there's a separate network of stations that were being used to monitor Mount Rainier. Those were in real time. And that data was not being fed into this and these other AFM systems. And likewise, the state data from these stations wasn't going in to contribute to the greater volcano monitoring network effort. So flashing forward 2 decades, in 2017, the USGS received initial funding for upgrading the RLDS, and we have continued to receive annual appropriations, and that's what's funding and motivating all the work I'm going to be talking about for the rest of this presentation. Specs for the new system include real-time data, and that gives us, at a bare minimum, it improves our ability to get that detection out to people within by 4 minutes. Also having broadband seismometers replacing the geophones, and also we added infrasound to improve detection capabilities. And the infrasound is something that over the last 2 decades, many researchers around the world have shown that mass flows writ large, but in particular, lahars at volcanoes can be recorded by infrasound sensors, and infrasound can be a very important component of helping you figure out whether the seismic signal that you're seeing translates to something that's moving on the surface or not. And also we've installed stations closer to the volcano to improve detection times, and we've integrated it with the existing volcano monitoring network. So it's all one grouping of stations, and that has expanded our abilities to provide automated lahar detection, but it's also expanded the capabilities of the volcano monitoring network. One important thing is that we've still maintained this distinction between the detection component, which is the USGS responsibility, and the warning component, which is Washington State Emergency Management Division and Pierce County and South Sound 911 are the 2 agencies that collectively handle the warning side of things. So just to give you a broad brushstroke sense of what we've done in terms of expanding this network, this is 2016. These red stations show the volcano monitoring network, the real-time component of monitoring in the Mount Rainier area. And then here's a picture of installations that we did in 2022 to get us to this point, which shows the network as it currently stands. And this is a graphic to give you a sense of sort of how we've done this. It's been slow. Parts of this have been slow and steady. There's been some definite leaps, like in 2022 when we did those installations at Mount Rainier National Park. And you can see the colors. The blues are for seismic stations. There's a lot more seismic stations now than there used to be. There's also infrasound that didn't used to be out there. We've added a few webcams, and there's also the good old tripwires. So this is a really impressive volcano monitoring network. It's not the average volcano out there that has 30+ stations. A lot of work has also had to be devoted to expanding, improving telemetry to enable all this data to get out in real time. And so what's not shown in here are stations that we also maintain that are just telemetry nodes. And it's required a lot of work on the part of our team to make all of this happen. So one of the things is that we've installed this network in the context, in context. So we've been looking at volcano hazards. One important context is the seismic context. Mount Rainier is, like I said at the start, it's an active volcano. The blue earthquakes there show all of the earthquakes that have been located by the Pacific Northwest Seismic Network at Mount Rainier over the last decade or so. And then the orange earthquakes show the what's called the West Rainier seismic zone, which is a north-south trending band of seismicity that looks kind of like it could be a fault. Nobody has ever found any actual places where the rock breaks the surface or where faults break the surface. But this is a known place where there's lots of seismicity. And one of the things that we've noticed since installing our network is that we've improved our ability to detect earthquakes on this. And so up here on the top, I've plotted the histograms showing numbers of stations, and you can see that from the left-hand side to the right-hand side, there's more earthquakes that are occurring per unit time in Mount Rainier now than there were back in 2015. And that is primarily a function of us having installed all these stations. And one piece of evidence for that is if you look at the purple circles and the green circles, to first order, I'll argue that those are occurring at about the same rate. Those are magnitude 1 and magnitude 2 type earthquakes. What's different is the orange circles, which are less than magnitude 1, and there's a lot more of those now. And that is a prime symptom of a network that has been improved, is that you really improve your ability to locate well earthquakes that are fairly small. So that's one thing that we've noticed, is we're seeing more earthquakes, or locating more earthquakes. Something else is that we've seen with this network is we've been able to record a number of surface flows, of mass movements. Most notably, there's lots of avalanches that occur at Mount Rainier, and we've seen them with the regular volcano monitoring network for a long time. But now that we've got this network out there that consists of seismometers and infrasound sensors, some cool things have come out of this. So here's an avalanche from January of 2023, and it's the seismic recordings and the infrasound recordings that are plotted right on top of each other, and you can see the tail and several of the impulses coming through. On the seismic side of things, this is something that West Eland's been doing, using relative amplitude locations to attempt to try to capture motion of this avalanche as it goes through time. So each of these dots reflects a 15-second time window, and the colors go oldest is the lightest, youngest is the darkest. And what this is showing is mass movement starting close to the summit to the north, and then going south, going downhill. So with just relative amplitude locations using our fairly dense network of stations, WES requires there to be at least 8 stations that would pick this up. So it's not something you can do with just a handful of stations. But this is the kind of thing that we're looking for being able to confirm in the middle of the night that we've got a lahar in our hands, is to be able to see some sense that there is something moving across the landscape. With the infrasound, that we've not just put out single infrasound stations. In many cases, we've put out infrasound arrays, 3-component arrays at individual stations. And this is a plot from a paper by Rebecca Kramer that's in review that shows the same avalanche, and shows back projections using the infrasound array from this one station, milled. And it's the same color scheme. The lightest colors are the oldest, youngest colors are the newest times. And these are minute-long time windows. And you can see the time scale on the right-hand side. So there's at minute 22, it's yellow. At minute 30, it's dark. And this kind of wraparound corresponds to a back azimuth that's changing in a systematic way as this avalanche goes past the station. And one of the goals, one of our scientific aims / operational aims, is to be able to marry these two kind of separate data streams, but are both looking for motion, evidence of motion, and be able to say, okay, does one see it? Yes. Does another one see it? Yes. Then bing, 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 we have something like that. And I'll show more examples of this with other kinds of flays, including this one. So we also, with these new stations, have also caught a debris flow. So this is a debris flow from 2019, August 2019, on the original sparse volcano monitoring network. And this really only showed up on one station. And in 2023, we had another one, same drainage. And this is plotted showing the same stations. And I should say the top stations are closest to Mount Rainier and the bottom stations are furthest away. And you can see that we've now caught this one debris flow, not a very big one, on 6 stations. So that's a big improvement and gives us some sense that we're kind of going in the right direction. So now I'm going to go a little bit into what may feel like a digression, but it's going to come back to science in the end, which is this the use of tripwires as as a way of giving you a sense beyond seismic noise. If nothing else, you can count on the tripwires failing. Or not tripwires being tripped by a large lahar. And this is right now part of what we consider to be the fail-safe part of this alert system, the automated part that goes off into the EOCs. But there's some challenges with these tripwires. And one of them is, well, they're good for confirming flows, but they don't provide any state of health information. They can be tripped by wildlife. And when they are, we don't know that they've been tripped. They are unusable after they've been tripped. And installation and maintenance is a real pain, as I hope this picture is giving you a sense of. It's hard to overstate how much trouble these things are to install and to maintain. So this is now work by Alex Yetzi that I'm going to present and try and do my best to say things as accurately as she would. Alex has been championing for the last couple of years an effort to look at laser rangefinders as an alternative to tripwires. And the motivation for this comes from our colleagues at the Hawaiian Volcano Observatory, who for the last number of years have used laser rangefinders for determining the height of a lava lake. And they've also used it for determining flow fronts, locations, and things like that. So Alex got to talking with one of these folks, and this idea was hatched to try it in the context of doing debris flow / lahars. So some of the benefits of the tripwires, the laser rangefinders, is that they are low power, they're low bandwidth, they're much easier to sight than tripwires. They have a very small installation footprint, especially relative to tripwires. They provide state of health information, and they will continue to function after they're tripped. After they're never tripped, but in the old system, in the tripwire system, once a lahar passes, it's not useful for any other like secondary waves that might come through because it's just tripped. So step one, Alex took this down to the USGS Flume in the summer of 2023 and installed it on the right-hand panel shows where they put it on this antenna mast and focused it right on the base of the flume. It's at an angle, so there's some geometric calculations to convert the distance of the laser rangefinder to flow height, which is the sort of one of the sort of ultimate easy ways to deal with these measurements. And I'm just gonna click here on this video, and I know there's no audio that will come through, but the audio doesn't matter. And the purple box shows its field of view. There's one pulse, and then there's another pulse. And so what this laser rangefinder found was success. There we go. It tracked the flow front as it came through, and then it continued to record after the flow front went past. This is in distance from the laser rangefinder, so it's sort of inverse what sort of you would expect. So Alex has done some geometric calculations and flipped things around so that it's now shown in terms of height of the passing flow front in terms of tenths of meters. So that was a success, and many kudos to Alex to overcoming some of us, mainly me, who were skeptical of this. So next step was to deploy this at Mount Rainier. And Alex did this last summer, along with folks from our office, including Emily Bryant and Craig Gabrielson. Just to sort of test this out, it was put on this antenna mast of one of our permanent sites along Tahoma Creek, which is a place that has a lot of debris flows, and I'll talk about that in a second. It was aimed right at the center of the creek. So a reason for going here is that Tahoma Creek is a place that experiences debris flows quite commonly. They're all glacial outbursts as far as we understand the mechanisms. These circles show the sort of groupings of them, and it's about every couple of years we get one. And in 2019 was the last one, and 21, 22, big melt years, very, very hot, dry, lots of expectation that we were going to get one. Never did, but keep on trying. And in 2023, when the laser rangefinder was out there, a debris flow happened. So that was incredibly awesome. And here on the right-hand side is a record, and I already showed this. This is the seismic amplitude record of that debris flow coming through. It also was captured by several of our infrasound arrays. This is a figure from a paper that Alex has written and is just submitted for review. And this is what is being shown here is the same kind of back azimuth projections as I showed before, with the light colors corresponding to early and dark colors corresponding to later times. And what all four of these, well, actually mainly three stations, COP, RER, and ARAT, are showing is this progressive sweeping downhill and the tracking of this flow front as it went past. And this is kind of what you would map out. So the laser rangefinder also captured this. And this graphic on the right-hand side shows the laser rangefinder on the top, the seismic amplitude in the middle, and infrasound on the bottom. And those are all from this one station, Tabor, which is shown on the left-hand graphic, the location. It's about a third of the way down the channel from where this flow initiated. So if you overlay all of these, you see that first order, the data sets match pretty well, which is pretty cool. If you drill into a little bit, however, there are some places where they diverge. One thing is that the seismic and the infrasound start picking up the sign of the flow earlier than the laser rangefinder. And the cool thing about the laser rangefinder is it's very clear when the flow front gets there, right at that black arrow. And one of the difficulties in working with seismic and infrasound data only is that they're measuring a lot of different noise sources, a lot of different places where seismic energy / infrasound energy is being generated, and it's all being scattered through the earth and scattered through the atmosphere. And so when it arrives at a single station, you don't necessarily know where that seismic signal or that infrasound wiggle, what part of the debris flow has caused that particular piece of noise. So the laser rangefinder makes it very clear when things come through. And so this was a success. And from this vantage point, the time scale in here is about 40 minutes. It seems pretty obvious where that the laser rangefinders are working. If you expand the viewpoint and look at 2 months of data, and Alex again gets lots of credit for exploring this question with lots of scientific honesty and integrity. This is expanding over 2 months, and the laser rangefinder is graphic B in this stack of 6 time series, and the red arrow points to the place where the debris flow happened. And in this context, it's really hard to have a sense that, yes, laser rangefinders are going to fix all our problems, because it's detecting a lot of other things as well. And one thing it's detecting is diurnal changes in that match up with air temperature. And so this corresponds with the sort of, I think, the generic experience of being out in places where there's snow and ice, and on sunny days, the river flow picks up in the afternoons. And the laser rangefinder showed this with the distances shortening as the river front went up with temperature. There's also these areas shown here in gray where there's lots of times when the laser rangefinder is showing something going through. These correspond to periods of time when there's higher humidity, and that our best guess right now is that this reflects some kind of cloudiness in the air, and lasers will reflect off of clouds. So that is a known issue, and it's something that Alex and others are really drilling in on to sort of think about how do we make laser rangefinders robust to this kind of a thing. And part of the answer is as with any other alarming system or alerting system, it's always that good if you can hang your hat on more than one type of data. And so in this situation, what would have made this a unique detection is a combination of the laser rangefinder and the RSAM from the nearby station. This was by far the highest RSAM value of the summer. So if you have an alerting system, a detection system that has if-elses or parallel detections that there's some smarts that are looking at these two, the power of integrating multiple data sets into a single alarm system is really what we're aiming at, and this is part of that. So for the last few minutes of my talk, I'm going to change the view from the data and zoom back out to thinking about or presenting some of the challenges that we faced in operationalizing the Rainier Lahar detection system. So number one is permitting. So this graphic shows the tan area, shows the outline of Mount Rainier National Park. And you'll notice that a lot of the red triangles that we added are inside Mount Rainier National Park. About 98% of the land inside Mount Rainier National Park is considered wilderness in the federally designated sense of things that's governed by the Wilderness Act, which has language in it that is strongly restrictive and really doesn't allow anything permanent, and especially doesn't allow the use of motors. So in order for us to be able to do this work, we had to go through a fairly extensive environmental assessment process that assessed the relative value from a public safety perspective of these installations, and also the impact from a wilderness perspective of the installations, and also some sort of mitigation steps that could be taken. Some statistics from this process: it took 3 years from when we submitted our initial permitting request to when we got a finding of no significant impact from the park. It was a $350,000 process. It was mostly for covering Park Service time, and there was a lot of time that was required by Park Service staff to do a lot of the fact finding, and also going out with us to look at the sites and assess the impact from a bunch of different perspectives, from the biologic, from the archaeologic, from the viewpoint, and so on. There were 2 periods of public comment, collectively bringing in about 60 comments, including several not inconsequential objections. And our permit request was for 12 sites, 9 were approved. So this was not a pass through by any sense of the phrase. That's one challenge. Another challenge is that in the event of an automated Lahar detection, right now the protocol is that our system detects things, the software decides there's a Lahar coming through, and alerts go off in these 2 24/7 emergency operation centers. There's now a CV over near duty scientist who is called for confirmation, because we have the real-time data. We can look at it and say, yep, that looks like a Lahar. And then after that confirmation is received, then alarms go out, are issued by the 24/7 EOCs. This has all been spelled out in a series of memorandums of understandings and memorandums of agreement between CVO and the Washington State Emergency Management Division, and CVO and the Pierce County Department of Emergency Division, Emergency Management. And this red thing here, this CVO Rainier Duty Scientist, is new. This is new for us. This was not part of version 1, 1998 system. And the expectation on us right now is that we be able to return confirmation within 2 minutes of when the alerts go off in the EOCs. And we achieve this right now by a couple of us, Wes, Alex, me, Ben, and 1 or 2 others, Ben Pauk, I should say, to take turns carrying a cell phone. And our our operational responsibility is to be able to respond to a cell phone call fairly quickly and get that confirmation within 2 minutes. We have spelled all this out, how we respond ourselves through standard operating procedures for what we do in different situations. We've iterated on these many times to come up with something that's relatively streamlined that we can walk through fairly fast, but also gets word out as quickly as we can. One thing that has been a part of this is developing a dashboard that we can call up from our phones or from an iPad or from a computer. And as soon as we call it up, this display is instantly generated, and there's a variety of graphics, a variety of ways of looking at seismic data, as well as infrasound for assessing visually whether an alert actually was caused by a real event or not. And this is all in the spirit of trying to avoid false alarms. In March of this year, we did a call down test of our protocols alongside Washington State Emergency Management Division and Southside 911 Pierce County to see how fast we could actually act in this kind of scenario where there's lahar that comes out of nowhere and wakes us up at 2 o'clock in the morning. The goal was for all of us to walk through our call down, see how long they took, and did they reach everybody. This is a call log from CVO's call down. It took us 17 minutes to go down our call down list following the automated detection, which was 22 minutes after the start of the event. And this is at 1 o'clock in the afternoon during the week when we were expecting this to happen. So 17 minutes isn't that bad, but it's likely it could be longer. So we have at 2 o'clock in the morning on a Sunday when we're not expecting it. So there's some things that we're still working on. And with our partners, some issues were encountered, but overall, word got out pretty quickly. So this is reassuring, but I think also everybody else was in agreement that we need to do this on a regular basis, probably annually, if not biannually, just to keep ourselves fresh. It's also important for the communities to know what to do when they get a word that lahar is coming. For one part of that is they need to know what a lahar is, and there's been a lot of effort to raise awareness by the USGS and by our partners. Another part of it has been, in this case, I'm showing pictures of an evacuation drill that was run by communities in the Puyallup River Valley, Ording and Puyallup in this case, to get school kids out of the way as quickly as possible. And in 2023, in March, there was a fairly large evacuation drill that we took part in that involved over 15,000 students that walked to high ground. And walking, not driving, because driving, there's accidents, driving, things get all bottled up. The best way to get out of harm's way is to walk, and also that frees things up for those who are not able to walk, hopefully frees the streets up more. Goal is for everybody to get to high ground within 30 to 40 minutes. That's based on things like this DCLAW modeling of David George and others that gives a sense of how much time people have to get out of harm's way. So the last thing I want to talk about is kind of where our minds are at right now in terms of thinking about our role in all of this. And this starts with thinking about this automated detection that goes off in the 24/7 EOCs. It's based on these sites with tripwires. Maybe down the road, the tripwires won't be there. There'll be laser rangefinders, but this is the place where our fail-safe, if all else fails, this is where the alert is going to happen. But the lahar is going to hit these sites 5 to 10 minutes after the landslide happens, after the start of the event. And what do we do with those first 5 or 10 minutes? When, that's time that is of value in terms of giving people more time to get out of the way. So in our scenario, playing out of scenarios, what we're pretty confident in is that we will see a very large amplitude signal, probably the largest thing that we will have seen recorded on at Mount Rainier. We'll also probably see a very, very loud infrasonic signal, and there probably will be evidence of mass movement. One of the challenges is going to be that we are not going to know the size, and we're not going to know the mobility, both of which have huge impacts on how far and how fast things go. These are two end member scenarios that come from David George's modeling. The left-hand side is what I've been calling, for lack of a better phrase, the large and fluid. This is the electron mudflow. This is a volume about 250 million cubic meters, high mobility. And this shows the first 10 minutes. The brown colors are 0 minutes after the start. The blue colors are 10 minutes after the start. And the left-hand side shows you that things have gone pretty far, pretty fast within those 10 minutes. They're already down towards the park headquarters and already well on their way to the electron. Contrasting that with the one on the right-hand side, the small and the sticky, this is a 50 million cubic meter, very low mobility event. This is akin to the Mount Rainier landslide from the 2010s. And same color scheme, 10-minute window, browns, 0 minutes after, blues, 10 minutes after. And what you can see is that at about 5 minutes, the event has stopped. There's no movement of a lahar past that point. So this kind of encapsulates the challenge, is that in the first 5 minutes, we're going to see stuff moving. And we're not going to be able to tell whether it's transitioning to a large lahar or not. And some of the things that we're sort of thinking through to ourselves is, what are we going to be looking for to help us out? One thing is going to be looking at these two stations, where at minute 5, the event will have gone past them if it's large and fluid, and it will basically have stopped or not reached them if it's small and sticky. And there's other ways that we're exploring for helping us out, sort of figure out what's going on in those first 5 minutes. But this is the place where this is pre-getting into these EOCs. It's pre-getting into our standard operating procedures with our partners. This is just about our Rainier duty scientist rotation, and what do we do? How do we handle this? How do we react? Recognizing that in this unlikely but highly potentially catastrophic event, that minutes will matter in terms of helping people get out of the way. So I'll just leave you with this summary. In terms of the build out of the RLDS, we're largely done. There's a few more stations that we are planning on installing around the volcano, but for the purposes of this automated alert part of it, we're basically done. Research and development is still continuing. I hope I've given you a sense of some of the algorithm development and testing and instrumentation that we are working on, and this will be part of this project for forever, because science moves on. There's always new things that we learn, new kinds of signals that we can look for, new ways we can process data, and that has to be a part of this project as we attempt to give ourselves more time and our communities more time to react. And then just lastly, I hope I've given you a sense a little bit of some of the operational requirements that we found are an added layer in terms of bringing to bear all the promise of the research that's been being done by lots of talented folks in the USGS and in the world in looking at mass movements, and in bringing it into a realm where there's a pathway for warning to get, or word to get to people, detections to get to emergency management agencies that can act and provide warning to communities that are prepared to act and know what to do. There's a fair number of steps in that, and I will leave it with that. Thank you.